Julie is a modeling engineer at Symbio and has a lot of fuel cell experience with several years now, and yeah, she's gonna tell us some more about that. Me too. Oh, still showing the old one. Now it's great. Okay, yeah, here you go.
Thank you. Thank you for your introduction. So today I'm going to speak about fuel cell stack calibration based on a separately tuned coefficient. So first of all, I'll present the company Symbio. Then we'll see what's the standard calibration method is for fuel cell modeling. Then we'll see what's the new method that we proposed. And I'll finish with the conclusion and future work. So first of all, who is Symbio? So fuel cells has become interesting for vehicle applications since the year about 2000, and since then Michelin was already working on the subject. In 2010, Symbio was created, so it was a small startup in Grenoble that was born in Grenoble. And in 2019, everything speed up. So it was when Faurecia and Michelin made a joint venture, bought Symbio. And at that time, we were 50 employees, and right now we are 750. So it was a huge growth. So in 2021, Symbio built the Hydrogen Academy. It is to train the employees on hydrogen system, and also entered in the Chinese as well as the US market. In 2022, Symbio made a joint venture with Schaeffler to build our own bipolar plates. And this year, Stellantis announced as a new shareholder. So the company is going very, very fast. So before 2021, we were able to produce about 500 systems per year. And today we have a capacity of about 2,500 systems per year. And so this is in our pilot plant in Vénissieux. And so next, we already moved to the new building, to the new Gigafactory. And the objective is to reach 50,000 systems per year by 2026. The objective is also to double this capacity by building a new Gigafactory in France, and to reach also 200,000 systems per year by 2030 at a global scale. So this is a huge project for Symbio. Symbio invested 1 billion euros in the high motive project. Part of it has been financed by IPCEI, so it's a European fund. And the objective of this project is to accelerate the industrialization and the mass production of fuel cell systems. So Symbio wants to meet every mobility need. So we have stack back from 40 kilowatts to 300 kilowatts. And our teams take care of the conception with clients' requirements, and also to the production, industrialization, and also the after-sale. So now I'm more speaking about the modeling team at Symbio. So we take care of all of the modeling chain. So we start at cell level with different models with varying materials, for example, with also CFD, mechanics modeling, to really understand deep electrochemistry and how the fuel cell behaves when there is a change in components and so on. We also model the stack. This is mainly to see to model the efficiency of the stack, the behavior of the stack as a component, and also then to integrate it at system level and see how the stack will interact with the other components. So, for example, Gauthier made you a presentation of how the fuel cell will interact with one component. We have finally the modeling of the vehicle level, where we basically want to model the power split between the fuel cell and the battery. Today, we're going to speak about the stack model. So first of all, I will present you the standard GT calibration method. First, so a fuel cell basically has hydrogen as an inlet, hydrogen and air as an inlet, and produces electricity, water, and heat. And so for this model, this is a simplified model on GT. So we used an electrical connection load type, and we have already calibrated the pressure drop and the water balance before. And we regulated the mass flow rate at the anode, cathode, and cooling. We've regulated also the relative humidity using a PID controller and via water injection. And we've calibrated the stack on a constant operating condition polarization curve. And we've validated on several polarization curve with varying operating conditions. So this is basically what an IV curve looks like. We have in light blue the maximum theoretical voltage that you can possibly reach. So this is basically the energy that is in the reactance. Of course, that would be too good to reach this theoretical voltage. So we first have the OCV losses. Basically, this is because not all of the reactants go to the catalyst layer, so we have some crossover, and those crossover will impact performances. And then we have the activation losses that can be modeled through the Butler-Volmer equation. Basically, these losses are mainly due to the fact that we need some energy for the electrochemical reaction to happen, and this energy has, is basically the activation losses. Then we have the ohmic losses. It is basically the proton resistance, so mainly in the membrane, so the resistance to the proton could go from the anode to the cathode. And this is modeled by the Springer model. And finally, the transport losses. So this is basically for the gas diffusion from the catalyst layer, from the channels to the catalyst layer. And this is a thick load that is used here. And for the standard calibration method, it is the catalyst loading that is calibrated for the activation losses, the multiplier of the water content for the ohmic losses, and the GDL porosity for the transport losses. So these are the first results with the standard calibration method. So we basically have good behavior for especially the calibrated IV curve. And we can see that we have, for most of the points, less than 10% error for the model on the whole range. So with specific error on specific points, typically high temperature and high humidity points. And now I'm going to present the Symbio calibration method. So basically, we didn't change anything for the OCV losses. The standard method is to take the current, the voltage, at 0 amp, so at 0 current. But for the activation losses, well, for all of the other coefficients, we choose to only tune non-measurable parameters. Because at Symbio, we have a lab where we can basically measure a lot of things, a lot of fancy things. And so, for example, we can have the catalyst loading, we can have the GDL porosity. So since we have the measurement, we won't calibrate it. And so all of this coefficient cannot be measured. And that's why we chose to calibrate those. So for the activation losses, we've basically calibrated the exchange current density, which is the required current to balance the electrochemical potential, the chemical potential, and the electrode potential. The charge transfer coefficient we've also calibrated. Basically, it is how much of the reaction goes in the reverse sense. So I will create H plus from H2, but how many H2 will I create from H plus? And that cannot be measured accurately, at least. And for the ohmic losses, we didn't change the coefficient. And for the transport losses, since we have access to the GDL porosity, we chose to calibrate the GDL tortuosity. So these are the results that we obtained. So up there we have the calibration method, and we've choose to also separate the different phases of the calibration. So we've calibrated the activation losses at low current densities, the ohmic losses at medium current densities, and the transport losses at high current densities. So here, it is the activation losses that are calibrated at low current densities. So we can see that we have low error on the first, at low current densities, which is completely normal, and the error rises at higher current densities. This is where we calibrate the transport losses. The ohmic losses. So now we're calibrating the ohmic losses at medium current densities. We've seen that we've improved the results a lot. Well, that's not surprising. And finally, we've optimized and calibrated the transport losses at high current densities. And basically, this is mainly what's interesting here. It is that on the validation data points, we've improved the results. So basically, we have a good model predictability, and we have for most of the, well, for 69% of the simulated cases, an error less than 2%, which is quite good. And also, most of the points, almost all of the points, fall within the range of -5% error. So now these are the slides to model comparison. And basically, we've seen that we've enhanced the results, especially with varying operating conditions, just by changing the way of calibrating. And this is, so we've managed to have almost all of the points that have an error of less than 5%. So now I'm going to conclude and present some future work. So in the proposed method, we've only calibrated non-measurable parameters. So and everything that we could possibly measure, we've measured it. And also the method is based on a 3-step optimization. So first, we optimize the activation losses at low current densities, then the ohmic losses at medium current densities, and the transport losses at high current densities, simply because this is the region where the activation losses will be predominant, ohmic losses also, and transport losses. And we've seen that the proposed method enhanced the predictability, especially when we've had varying operating conditions. And as a future work, what we are doing now is to fine-tune the coefficient with data including varying operating conditions, and find an optimum of required data for accurately calibrate a fuel cell model. And I thank you for your attention, and don't hesitate if you have any question.
Yeah, thank you very much, Judy, for the in-depth explanation of the calibration process. Are there any questions in the audience? Really? Oh, okay.
Yeah.
Have you studied the root cause why some of these cases failed?
So some of the cases failed mainly because basically it is during dried cases. So it's either high temperature or low humidity cases. And basically that's why we want to calibrate it also with varying operating conditions, because here we have a huge difference between the operating condition in which we calibrate it and the real operating conditions. About 20 degrees difference, that's why.
Any other questions from the audience? Yeah, maybe then I have a quick question, Julie. Also, are you also planning to look more in detail into the water crossover and the water balance of the stack, or is
Yeah.
it?
Yeah, sure. Of course, this is coming in the few next days, actually. So, yeah. That's.
Okay. All right. Looking forward to supporting you with that, just like we did BMW. And as Stefan mentioned. Yeah. All right, then. Thank you very much.
Thank you.